Yeah, good afternoon, students. It's my pleasure to introduce this classroom discussion topic on the applications of a stack, that is a recursion. So now I would like to share my screen. Hope my screen is visible to you. Yeah. So this is a week 5 lecture 1 applications of stack. First application we are going to discuss in this CDT, that is a recursion. So the summary of the previous CDT is that we discussed about the implementation of multiple stacks in a single array. That is, more than one stack we can implement in a single array. Suppose an application requires two stacks. So instead of defining two separate arrays, so we can define a single array and we can implement two stacks within that single array. So such that one stack will grow from right to left and other will grow from left to right direction. So that is what we done in the previous class room discussion topic, implementation of the multiple stacks. So not only two stacks we can implement k number of stacks we can implement in a single array by dividing that array into k number of slots such that each array may be of size n by k. So that is the another important mechanism how these multiple stacks are implemented. Now coming to this today's topic, it is a very important topic related to that the applications of this stack data structure. So this is the one of the primary application of the stack is the recursion. So the lecture objective is that this session will develop the students' knowledge on the applications of stack, which is one of the important application is recursion. The lecture outcome is that after completion of the session, students will be able to develop the code using recursion for solving a given problem. So what do you mean by recursion? So recursion, which is an implicit application of the stack editing. Okay, so whenever we are writing a recursive function, implicitly stack data structure will be used, whatever we have defined within the program. So you need not require to worry about all the implementations of the stack operations. So implicitly, the system stack is used when we are writing a recursive program or recursive function. So a recursion is nothing but a recursive function is defined as a function that calls itself to solve a smaller version of its task until a final call is made, so which does not require a call to itself. So recursion is nothing but calling the same function repetitively until some base condition is satisfied. So since a recursive function is repetitively calls itself, so it makes use of a system stack to temporarily store the return address and the local variables of the calling function. So the system stack is implicitly used when we are making the recursive calls. So every recursive call is going to be stored in a system stack. So in that recursive call, whatever we are storing in the system stack, what we are going to store? We are going to store the return address as well as the local variables at that particular call. What are the local variables are there and their values are there. So this together return address and the local variables is called it as an activation record, we can call it as. So this activation record will be stored in a system stack for every recursive call statement. Fine. So in recursive function, a complex problem is divided in terms of simpler problems, and the simplest problem is given explicitly for the solution. So we are taking an example here to calculate the factorial of a given number n factorial. So generally the definition of n factorial is nothing but the multiplication of the numbers, natural numbers starting from 1 to that given number. For example, you take 5 factorial, So 5 factorial is nothing but 1 into 2 into 3 into 4 into 5. So if you do this multiplication starting from 1 to 5, then we are going to get it as 120. This is 5 factorial. So this computation or this definition of the factorial problem is called it as iterative definition of the problem. Okay, it is called it as a iterative definition of the problem. But when we are coming to the recursive definition of the problem, that means defining the problem in terms of the smaller problem itself. So this is what we are defining n factorial in terms of again factorials. So n factorial is equal to n into n minus 1 factorial. So smaller task, smaller subproblem we are defining. Again n minus 1 factorial, we can define it as n minus 1 into n minus 2 factorial. This is called it as a recursive definition of the problem, factorial problem. So you can solve this problem both in iterative approach as well as a recursive approach. So 5 factorial, you are specifying 5 into 4 factorial. Again 4 factorial, you are specifying 4 into 3 factorial. Therefore 5 factorial is equal to 5 into 4 into 3 factorial. Similarly 3 factorial, you are specifying it as 3 into 2 factorial. So 2 factorial, you are specifying it as 2 into 1 factorial, where 1 factorial is equal to 1. So here we are stopping the definition of the factorial problem in terms of the factorial itself. So this is what we are calling it as a base condition or a base step or terminating condition of the recursive process. So like this, you can see in this also how we are computing this 5 factorial recursively. Fine. Hope you got that idea. So every recursive function must have base condition and a recursive case. So these are the two steps every recursive function will have. So for example, if you take a factorial function, the base case is that when n is equal to 1, because 1 factorial is equal to 1. So the recursive case for the factorial will call itself but with a smaller value. So factorial of n is equal to n into factorial of n minus 1. This is what we are calling it as a recursive step or recursive case. The base case is that 1 factorial is equal to 1 is the base case. Got the point? So this is every recursive function must and should have base case as well as recursive case. Now this is a programmed for calculating of the factorial of a given number using a recursive function. So we are declaring a function. So fact function, we are declaring that such that it will take an integer argument and returns an integer. So fact function is going to take an integer value as input and returns an integer value as an output. Fine. So in the main function, we are just calling enter the number. So we are reading the number here. Suppose this number value is if you are given 5. Okay. Then we are passing this 5 value to the fact function. So because fact function is returning a value, so we have to assign that function call statement to an appropriate integer value. So val is equal to fact of num. So once you call this function, this is the function call statement, the control will transfer to the function definition here. So this n value, it is copying it as the value 5. Okay. Then if 5 is equal to 1, no. Then we are calling that 5 into factorial of fact of again 4. So we are calling this fact of 4, we are calling that. Got the point? So now this is what we are calling it as a recursive call. Again, the function is again called here. So now n value is copied it as a 4. Now again, this fact of 4 is stored in the stack. This call will be stored within the stack from the main function you are calling. Na? So this is stored in the system stack. Then next, whenever you are calling fact of 4, now it will be again stored 5 into 4 into f of fact of 4 minus 1, that is 3. So this will be again stored in the system stack. So this is again second activation record that will be stored on the system stack. So like this, it will store the set of activation records for each and every recursive call. One record will be stored in the system stack. until when we reach that n value. That means whenever if you are calling this fact function with 1, then you are satisfying the base condition. This is what we are calling it as a base condition. You are satisfying that, so that we are returning 1. So once this base condition is satisfied, then what we are doing here is that we are popping off the activation records and we are backtracking these values, and we are back substituting these values to compute this 5 factorial value. Fine. So like this here, finally we are going to get it as 5 into 4 factor value is known here in the previous call, and we are going to get it as 120 as an output, and that value is returned, 120 value is returned to this val variable. Now we are printing this val variable in this. So this is a simple example of finding the factorial of a given number using recursive function. Fine. So now we will see a call stack trace. We will see here with this an example. Fine. So this is what the reflection spot. So what is the data structure used to implement a recursive function call? Anyone can answer this? What is the data structure which is used in implementation of the recursive call? Fine. So the implicit data structure that is used in recursive function call implementation is stack. This is the right answer. Fine. So if you are not able to answer this question, please watch the video from the beginning. Okay. So any doubts you have in these recursive functions? Fine. So after completion of this session, the lecture outcome will be revisited here. Students will be able to develop the code using recursion for solving the given problem. So summary of this today's session is that so we had defined what is a recursion. Recursion is nothing but calling the same function repetitively until some base condition is satisfied. Recursion will have base case as well as a recursive step. So the base case is the problem which is simple enough to solve directly without making any further calls to the same function. And recursive case is in which the first problem at hand is divided into simpler subproblems. Second, the function call itself calls itself but with subparts of the problem obtained in the first step. Third, the result is obtained by combining the solutions of simpler subproblems. Therefore, recursion is defining large and complex problem in terms of smaller and more easily solvable problems. So the recursion, which is an implicit application of the stack. So stack ADT is implicitly used by the recursion. System stack is implicitly used. Fine. So this is a lecture level practice problem. So everyone has to solve this in the class itself. So find the GCD of two numbers. So the recursive definition for computing the GCD is given here in this particular definition. This is a Euclid's algorithm that computes the GCD of two given positive number. GCD of m comma n is equal to n if n divides m. Otherwise, GCD of n comma m mod n. So this is a recursive definition. So try to write a program to calculate the GCD of two given positive numbers. Okay. So these are further readings on this particular topic. So you can refer this classic data structures by Debasis Samantha. Fine. So thank you one and all.